All right, we're back at it again, boys and girls. We are now on assignment 1E. This is dealing primarily with inverse functions. Inverse functions. So again, just a general key idea of what an inverse function is. If I have a function, y is equal. Let me start off with an f of x. This is just a brief example. F of x is equal to 2x plus 1 or something like that. Some basic idea. The idea behind an inverse function is we understand that this f of x is actually the letter y. So I think of it like that. Now, what an inverse function is, every x becomes a y and every y becomes an x. So the points of something that, so if this is just a normal equation that comes with a point that xy, that implies that the inverse function is a yx. So another concrete example of that is if you have a graph that is that has a point 2, 3 somewhere on the graph, 2, 3, that implies that the inverse will have the point 3, 2. Sorry, my board doesn't work very well up in this corner. It implies that the point has 3, 2. So these 2 points right here are inverses of each other. All right. What you'll notice is it will be symmetrical about a line that is a y is equal to x. So it's symmetrical about a 45 line. Okay, back to my other example that I was talking about. So if I know that y is equal to 2x plus 1, that implies that the inverse is x is equal to 2y plus 1. And then what is asked of us is just to manipulate this new inverse equation and resolve it for y. So I would subtract 1, and I would divide by 2. Okay. And then understand that this is an inverse. So this is technically an inverse as such. Okay, so that's the idea of taking an inverse and understanding an inverse. So the key idea is from your base equation, you just turn every y into an x and every x into a y. And that generally gets you what the quote-unquote inverse is. And then it's just math to resolve for y to put it in a version that people like. Okay, that's an inverse. All right, so here we go. In exercise 1 through 8, show that f and g are inverse functions analytically, numerically, and graphically. All right, so one of the tests that show that something is an inverse is these facts right here. If f of g of x and g of f of x are both equal to x itself, then they are inverses. So this is a analytic test. So let's go with this this option A, and we're going to show that f of g of x is equal to x. So in this first equation, we see that the f is the big outside function. So 5x plus 1. Okay, so that is the f. Now inside of that f, I put g, which is x minus 1 divided by 5. All right, so simple math. I see that if I multiply and divide by 5, it goes away. So this is x minus 1 plus 1. And then I see a minus 1 plus 1. And so I am seeing that this is indeed equal to x. So that is true on that portion. On the second one, I see that g is the big equation. So this is x minus 1 divided by 5. And the f that I'm putting inside that g is 5x plus 1. And I'm going to show that this is equal to x. All right, so dealing with the numerator, nothing is multiplying in, so this is a plus 1 minus 1. So this is a 5, oops, it's supposed to be in blue, 5x divided by 5. 5 eliminates the 5, simplifies the 1. And indeed, yes, x is equal to x. So we just showed analytically that they are inverses. And so this is one of the tests that if you take an inverse and you embed it into the other, it will be equal to x. All right, show that they are inverses. And so what this next one is, I'm just going to kind of drop this down so I can write a little more clear. Right. So in this one, what we're going to, in essence, show is if I take various points of this f equation, so I'm just going to say what is 0, 1, -1, 2, -2, 3, or something like that. And I am going to show that the inverse, g, will have the exact same points, but just opposites. So in essence, if I show if f has the points, you know, like 2, 3, and -1, 5, and 7, 4, or something like that, its inverse, okay, its inverse will have the exact same points, but just opposite. So I will notice that they are going to be the exact same, except the x's became the y's and the y's became the x's. And so that's what this is. That's what I'm showing here with these tables. Okay, so 5x plus 1. Okay, those are the 5x plus 1s. Now what I'm going to do is I'm going to take these f of x's and I'm going to be making it the x of the next. So 1, 6, -4, 11, -9, and 16. So I'm making that the x of this next, and what I'm hoping to get out of this is the g of x will be the x's of the original. So here we go. So this is going to be 0, 1, -1, 2, -2, 3. And so, yes, indeed, I did show that if this is x and y, and this is x and y, notice how the x's and the y's switch places. Okay, last but not least, we want to graph and show that they are inverses via a graph. And so what that implies is it'll be symmetrical about this dashed line. I'm going to write this g of x into something that I can maybe understand just a little bit more. We'll see. Okay, so the first has a y-intercept of 1 and a slope of 5. 1, 2, 3, 4, 5. 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so here is that dude right there. And let's go ahead and graph the other one. dash, or why not? All right, so -1/5, then up 1, run 5, up 1, run 5, 1, 2, 3, 4, 5, 1, 2, 4, 5, down 1, still on the top side. So this is just -1. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Such. And so they should be symmetrical about that. So like any point that is concretely, like this is like 1, 2, 3-ish, 3.5-ish to that. This should be 3.5 going the other way on this same thing. So half, 1.5, 2.5, 3.5. No, I'm sorry, it's 2.5, 2.5. 1, 2.5, 1, 2.5. Yeah, so that is, it's looking rudimentarily good. All right, so there's a flurry of these problems, so I'll kind of hit the gas here and just kind of hopefully fly through these problems. These go out in thirds, so that's a 1. So 2 would be 8. I'm sorry, I'm stupid. Sorry, I just regular graph. Sorry. 1 would be 1, 2 would be 8, 3 would be 27. 1 would be 1, -1, -2 is -8. All right, so we have that, and then the third root. It is having problems with my pens today here. Let's see if I can kind of make this a little bit better. And so third root is again 1, 8, 1, 8, and there you go. And so we see that they are symmetrical. An example would be looking at these. They should be inverses of each other. And so going directly to the diagonal, I see that this has a distance of 1, 2, 3 at the diagonal, 1, 2, 3 at the diagonal. It works out just fine. Okay, continuing on. F is x minus 4, okay, and what I'm putting in is the g, so that's x squared plus 4, so 4 minus 4, and then square root square, ta-da. G is x squared plus 4. I see that the f is inside the g. Square root of a square of a square root, x. And then I see the minus 4 plus 4. Okay, thinking of this square root, these are x's that they have to be big. The smallest that this number x can be is 4. The smallest x can be is 4. Just looking at the graph of the f of x, I see that it's going to be shifted over 4, and it does something like that. So the smallest x can be is 4 to make this work, because the second equation is also saying that x has to be greater than or equal to 0. So if I even did make x is equal to 0, it's going to be 4. So the smallest it can be is 4. So in that case, I'm going to start with something like 4, and then any number bigger than 4 is what I'm looking for. I'll just try to choose numbers that will create good square roots as well. Okay, so numbers bigger than 4, and then plugging and chugging. So this is going to be 0, this is going to be 1, this is going to be, I don't know why I chose a 6. This is going to be square root 2. Like, whatever. silly number to choose. That's going to be square root 2. 13 is 3. I'm just gonna. Yeah. Oops. So if I'm going to produce a 2, this is going to have to be 8. That's visual. 3, 20, 16, 4, 29, 25, 5. There it is. Steal those numbers and show that it is an inverse just via points. So 0 plus 4, 1 plus 4, 4 plus 4, 9 plus 4, 16 plus 4, and 25 plus 4. 25 plus 4. Okay, so inverses they are so far. Here, the f of x was x, x minus 4, square rooted, and the g, let me change colors here, blue, g of x is x squared plus 4. All right, so symmetrical about this dashed line. So as I said, this is a square root picture. The thread is a square root picture, right 4. So right 4, 1, 2, 3, 4, and then it's a 1, 3, 5 going out that direction. the g is an x squared plus 4. So that is a parabola up 4, 1, 2, 3, 4. However, they very clearly state that this is only applying to x's greater than or equal to 0. So yes, the parabola should do something like that. However, we are not looking at x's that are less than 0. So this is just strictly applying to the greater than 0 x's. So 4, and then again, it's 1, 3, 5 going up that way. Just continue the odd numbers. And I do see that this is an inverse, so I'll take this point. And this point, for instance, this is 1, 2, 3 from the dash line, 1, 2, 3 from the dash line. It's matching up symmetrical about that 45. So again, you can take other points if you want. 1, 2, 1, 2, 1, 2, 1, 2. They're matching up symmetrical to that y is equal to x. Ugh, jeepers, creepers, more. Here we go. So the f is 1 over x, and this is a 1 over x. So the way that I see that, this is going to be equal to x. So this is 1 over 1 over 1 over x. And so this multiplies to there, that multiplies to there. And so we see that this will be x over 1. That is indeed equal to x. And this should be the exact same problem. So the g is 1 over x. And then the f is inside, so this is 1 over x. Show that that is equal to x. So 1 over 1 is over 1 over x. So the denominator is going to be 1. The numerator is going to be x. X. As such. So I know that the f of x is 1 over x, and the g of x is also 1 over x. So picking out some good points, let's go 1, negative 1. Can't pick 0. Can't choose a 0. Doesn't work. 2, negative 2, 3, negative 3, something like that. And so this is going to be 1, negative 1, 1 half, negative 1 half, or 1/3, negative 1/3. Steal those. And put it into the g. So again, if it's a denominator, so g of x is the same thing as saying x to the negative 1, so it's just a reciprocal of what is already there. So it works out. It's just a reciprocal of what's already there. Show that 1 over x is the inverse of 1 over x, and so that will have a point there and there. So 1 over x looks like this. So there is the 1 over x, and the inverse is also a 1 over x. And notice that the blue does match up with the red. 1 to the horizontal, 1 to the horizontal. This is at what, a half? So this is kind of hard to show, but it matches up. Take my word for it. It matches up. It's like equidistant. Going to the opposite side, it's equidistant. It's a reciprocal, like, so you could fold this side to that side, and this side to that side, and it would fold perfectly along that line right there. It's all good. All right, finally done with those problems. Let's move on. Use the horizontal line test to determine if a function is one-to-one on the entire domain, therefore it has an inverse function. So you're probably familiar with the vertical line test. What the vertical line test says is this: if I have a random graph of something, is that quote unquote a function? Is that a function? And what you do is the vertical line test. So no matter where I draw a vertical line, the vertical line only touches the graph at one point, or no points, but it can't touch twice. So the picture that I have drawn here is a function, whereas if I had a graph that looked something like this, no, that is not a function. It does not pass the vertical line test. Now, to do an inverse, it's the exact same idea, but you do the horizontal line test. Like, I'll steal these pictures too. Right, so if this picture looks like, ooh, it's being black, looks like this, is that, does that have an inverse? Does that have an inverse? Question mark. Well, you can do the horizontal line test. And so if I draw a horizontal line, I see that, oh man, it intersects my graph at 3 places. It fails the horizontal line test. So no, this is not one-to-one, and this does not have an inverse function. This will not have an inverse applicable. This picture over here. Okay. Does this pass the horizontal line test? Yes, this does pass the horizontal line test. This would have an inverse. Going that direction, I hesitate to say that it has an inverse, but anyways, that's what the horizontal line test. So here I see that the horizontal line test does work out. The original is a function. So yes, this does have an inverse. Next one, yes, this does have an inverse. Nothing is touching twice. Everything is just touching once. Sine, no. Does not pass the horizontal line test. So no, that does not have an inverse. This weird looking graph, no, it touches twice. No, this does not have an inverse. Then again, this is just applying ideas of LNs and E's. We talked briefly about it last lesson. So I see that this Ln eliminates this E, so this is equal to 2x. This Ln eliminates this E. This leaves us with 2x minus 1. Pretty simple. E to an Ln, same idea. This is 5x plus 2. E to an Ln, this is the square root of x. These are crazy easy problems. Ln E, so this leaves us with 1 plus 2x as such. Looks like we're going to be using our calculators. I noticed that because they say solve accurate to 3 decimal places. I always go to 4 decimal places, just heads up. X is equal to 4. That one's pretty easy. 2x is equal to 3. That implies that x is equal to 3 over 2, aka 1.5. Okay, here in 107, I need to eliminate this. So x is equal to e to the 2. E to the 2, I'm not that good at math. Here's where I need my calculator. E to the 2. E is written right above the ln button, so you have to hit. I'll show you how I do it. So E is written right above this ln button, so I have to hit second ln, and then that brings up my e to the, and so here I go, e to the second power, and that's what that is. Okay, this one, I need to get rid of this E, so I need to, oops, sorry, a little wonky there. ln, and so that is an ln of 8. And then continue my mathematics, x is equal to ln of 8 minus 2. So let's go ahead and get a number to that. So ln of 8, make sure you close that down. So you tell the calculator that I'm only taking the ln of 8, not the ln of, in essence, 6. I'm not taking it 8 minus 2. So the ln of 8 minus 2. Zero 794. There it is. All right, solve the inequality. So again, just more solving stuff. Again, if you multiply or divide by a negative, then you switch the inequality. So x is greater than ln of 5. Oh, the only problem there. Cool. So that's it. Not too bad. Just thinking of inverses. And again, what the idea of an inverse is if I have an equation, an inverse is switching all the y's to x's and all the x's to y's, and then resolve it. So so thus you can have yourself an inverse. All right. Have a good one, everybody. If you have any questions, make sure you ask during our class time.